Hello, IB. We just want to go over what we did in class last lesson when we looked at section 15a and the whole simple way of finding the derivative function. So in other words, coming up with that simple rule. It's springboarded out of what we've done in chapter 14 with different functions and using first principles and looking at graphs. And what we saw is that when we have a derivative here, that the original function is just a constant, the derivative function f dash x is 0, which means if the graph is horizontal and we've got just one line going across, here's our line, then anywhere along that line, if this is at 5 in this case, then the derivative or the slope is 0. So no matter what x you choose, the slope of that horizontal line is always 0. In this case here, where we had 3x plus 2, I'll draw it on the same graph, we've got a straight line. So anywhere along that straight line, probably not quite to scale, anywhere along there, the gradient is 3. It's constant throughout it, so our derivative function was 3. In here we discovered that for the quadratic, that if we have a quadratic function, in this case x squared minus 3, there, then the derivative function says, what's the slope like? Well, the slope here is 0 because it's at a minimum. But here our slope is always positive and here it's always negative. And in fact, we found out from first principles that that is our derivative function, y equals to 2x, meaning if I want to get the derivative at any point for x, I just simply go that x value times 2, and that tells me the slope of the tangent at that point. So with this next one here, we could see that one's not as easy to see, but our rule was that the power of 2 became a power of 1, and it was always 1 power less when we found the derivative function. And in fact, our simple rule says get the power of 2, multiply it by whatever our coefficient is, and then subtract 1. So that meant the derivative function for this graph would be 2 times 4 makes 8x, and because we've subtracted 1, this has now just got a power of 1 on it. Same story here, the exponent here is 1, so 1 times minus 1 makes minus 1. 1 minus 1 is 0, and we found the derivative for a constant like plus 2 was always 0, so that constant disappeared. And our derivative function is 8x minus 1. Same story with x cubed. What's our power? It's a 3, so we multiply it by the coefficient, which is 1 in this case, so we go 3 times 1 is 3. Subtract 1 from the power, and we end up with 3x squared. So we put that all together with this more complicated one. 4 came down the front, 4 3s are 12. Take away 1 makes power of 3, so we get 12x cubed. 3 times minus 2 becomes minus 6x squared, because the 3 becomes a 2. Here, the power of 1 on x. So in this case, our coefficient is 3 over 2, positive 3 on 2. So 1 times 3 over 2 becomes 3 over 2. Power of 1, you take away 1, so it becomes x to the 0, which we know is just 1. So it's just plus 3 on 2. Right, and that was reminding you how we can write that in different ways to remind you that that's just the coefficient. So our simple rule is get your power on n, multiply that down the front with whatever your coefficient is, and then subtract 1 from the power, so it's 1 less. So any constant becomes a 0, any power of n becomes n x to the n minus 1. If our function is multiplied by some number, then we just multiplied it. That was like looking at this example where we had a 4 in front. We're just going 4 times 2. And then if we're adding up little functions in x, we can just differentiate them one at a time. We don't need to do anything different there. So that's like here where we've got 3 terms and we just differentiate each term at its time. So here in this one, let's do this one together now. So x cubed, the 3 comes down the front, so we get 3, because the coefficient here is 1. X, it was cubed, it's now squared. Next one, 2 times minus 2, so we get minus 4. It was x squared, so it's now x to the 1, but we don't need to write the 1. That's a constant, so that becomes a 0. We don't need to write anything. So there's our derivative function. Here, the 4 came multiplied down to get 20, x cubed. 2 multiplies down to get minus 6, power of 1 on the x. Here, the 7x is just the coefficient 7, because we get x to the 0, and that's 1, and the 2 disappears. So now, if we want to find the gradient of the tangent to this function when x is equal to minus 1, then all we now need to do is use our derivative function, substitute in minus 1, and put it in brackets to remind you you're cubing the minus 1, etc. And we come down to see that our function has a gradient of minus 7 when x is minus 1. Our original function was a quartic, so that means it could look something like this blue wiggle. Don't know, we haven't graphed it properly, we've just done a rough guess at what it could look like. But this tells us that if this gradient is minus 7, then it's somewhere in these regions where the gradient is negative. So it's somewhere up along here where it's got a negative gradient, or somewhere along here where the gradient is negative. There the gradient of the function is positive, and at this point it's 0 at the minimum. So it's definitely not there. It's somewhere between that maximum minimum and that minimum, and where it keeps going on forever. These ones here are a bit harder. In this case, we've got our x squared, but it's in a denominator. So if you've got it in the denominator, rewrite it with that power of minus 2, and then we can just use the same rule. So we do the same thing of get our minus 2, multiply it down, so we go 4 times minus 2 is minus 8, but now we still subtract 1, minus 2 minus 1 makes minus 3. Alright, same story here, turn that denominator of x into x to the minus 1, so minus 1 times minus 5 makes plus 5. Take away 1 from our exponent, so we get minus 2. Then always turn it back into the way it was given to you. If it was given as fractions like this, turn it back into the fractions. So we get minus 8 divided by x cubed and 5 divided by x squared. Same story here, cube roots and square roots. Remember, as an exponent, they're 1/3 and a half for a square root. So this is 6 times x to the 1/3. Multiply it down, so 6 times a third is 2. Subtract 1, I told you we had to be good at fractions. So 1/3 minus 1 is minus 2/3. Here we've got minus 5x to the minus a half, because it's now in the denominator, which makes it negative. Half, because it's a square root. So minus 5 times minus a half is plus 5 on 2. Subtract 1 from up here. So we want a half, minus a half minus 1 is minus 3 on 2. Let's turn it back into how we got it. So the minus 2/3 becomes in the denominator, cube root of x squared in the denominator, 2 is in the numerator. 5 over 2, 5 in the numerator, 2 in the denominator. The minus says x to the 3 on 2 is in the denominator. The denominator here of 2 means square root. The cube means x is cubed. Alright? So same rule, but just a bit more complicated. Here, if we want to find the values of x where the gradient of this function is 0. So whereabouts does this, we're going to talk about more, have a minimum or a maximum where it's got a gradient of 0? The first thing you should look here and go, oh, well, we can't have x equal to 0 because we have x in the denominator and we can't divide by 0. When you want to differentiate this, an easy way is simply to break it into the two fractions and simplify once you've recognised that domain restriction. So we have 8x to the 4th over 4x minus 3x cubed over 4x. We can simplify by cancelling. Now we can differentiate, so the 3 comes down, we get 6x squared. 2 multiplies down, so we get minus 6 over 4 to the x times x. They cancel further, so now we come up with our derivative function here. Whereabouts does this derivative function equal 0? Like, what x values does this happen at? So we now want to make 0 equal to this. So you can use various ways of solving that, but basically here we decided to multiply by 2 and then factorise it, because if it's a quadratic, you can either factorise or quadratic formula. So when we factorise, we come out with either x is equal to 0 or x equals a quarter. We saw at the beginning, our original function, we can't have x equal to 0. That's not possible. So that's not a solution. So this is our solution, x equal to a quarter. So that means in this function here, if we graphed it, when x is a quarter, we will find the graph is either has a maximum, all right, because the doesn't quite line up, because that tangent is horizontal. It's all joined together. So let's just erase that. So we're going to see that it's either going to have a maximum where the tangent is horizontal like that, or there could be a minimum where the tangent is horizontal-ish. All right, and we're going to do a lot more work on that in the next chapter. So let's look at this one. This is new. We didn't do this one in class. Here I've got a function with 3 variables in it. Our main variables are usually y and x. But in this case, we've got an a in it. So when I see this, I want to differentiate the function in y. So this y means we're differentiating this function with respect to x. So here in this case, we're going to consider that our a is a constant. In other words, ignore it. Just pretend it's a number and treat it the same way. So now the 2 comes down the front, so we get 2a cubed x to the power of 1, because we've subtracted 1. Differential of plus x is just going to be 1. That's the coefficient. 2a is just a constant, so it disappears. All right? Whereas here, we're now saying differentiate y with respect to a. So in this one, we're going to consider that x is like a constant. It's not going to be differentiated. So it's like we've changed our variables. So now, if I look at here, with respect to a, I've got a cubed. So now my 3 comes down the front. I have x squared. It doesn't change because I'm not differentiating with respect to a. And the a was a power of 3. It's now a power of 2. The plus x is like a constant, so it just disappears. So I'll put a 0 there this time. Now the 2a, a is like a variable. So now the a disappears because it's a power of 1 on that. And we're left with 2. So our derivative function in this case is 3x squared, a squared plus 2. So the little message in this one is always look carefully what you're differentiating with respect to. In this case it was a, and in this case it is x. All right, so that's just a little variation on the theme. And the last one here, S equals ut minus a half at squared. Some of our physics people will hopefully, all our physics people should hopefully recognise this. So S of t is our abbreviation for displacement. And we're going to be doing a lot of work with displacement and motion in this course. So, displacement. If I differentiate, I want the change of displacement with respect to time. So time is our variable, so that t disappears and we're just left with u. The 2 comes down the front. So 2 times 0.1, oops, is plus 1. So we get plus 10. So it's u plus at. So hopefully our physics people will recognise that as v equals u plus at for our velocity relationship. And what happens if you differentiate now our velocity with respect to time? Then u is just a constant, so that becomes 0. T comes, the 1 of that comes down the front, and that becomes t to the 0, and we're left with a. So dv dt, so d, equals a, and that's our acceleration. So that's how we're going to be linking together all the motion and calculus. So thanks for listening. Hopefully that was a good summary of what we did in class last lesson. We'll keep this one, copy it down, have a go with it, and see whether you can come to class with an answer for that one. All right, thanks for listening. Bye for now.